Okay, so this is going to be an additional video on some discrete random variable stuff. At the very end of it, I'll put another example of a Bayes theorem problem that we talked about in class today. It's kind of interesting, just another example. I'll do some more board work with it, so you'll get to see it worked out a little bit more. But for now, let's jump into these week 5 lectures, which I'll get posted on Canvas, so if you want to follow along with the slides as you listen to this, you can. The very first thing we're going to talk about is maybe we have some random variable x, right? The first thing we're going to deal with is that it's a discrete random variable, right? So right now we're dealing with discrete random variables, and they can take on any integer value, right? We'll kind of be working with examples like that. So we'll have a cumulative mass function that tells us the probability that a random variable takes on a value that's less than or equal to some value for lowercase x here, right? So obviously, if I'm looking at, let's say, the number of children in a household, the probability that if I chose a household at random, that it has one or fewer children, right? So I put 1 in here, would be relatively low. If I put in that they have less than or equal to 20 children, well, that's got to be pretty close to 1, right? So as we get to higher values, this cumulative mass function will take on the value of 1. As we approach lower values, this cumulative mass function takes on a value that's closer to 0. Right? So this is the idea there is some cumulative mass function. We're also going to have a probability mass function that's going to tell us the probability that x takes on one specific value. So if I'm thinking about this, this would be as simple as, the cumulative mass function tells us the probability it's below a value. Probability mass function is that probability it takes on one specific value. Okay? So I have this kind of Purdue Football wins going back from 2015 to 1980. The number of wins that they have, I just counted up. I basically have, everything we're going to be doing with this discrete random variable until we get to specific discrete random variables looks just like what we were doing with relative frequencies and building frequency distributions. So I have all the possible outcomes, 0 through 12 wins, and I have the number of seasons where they had 0 wins, the number of seasons where they had 1 win, the number where they had 2, so on and so forth. Once I have these frequencies, I very easily can convert these to probabilities. It's just like what we did before with relative frequencies. How do I turn a frequency into a relative frequency? I divide by the total number of observations. So I just go through, I divide every single one of these frequencies by the total number of observations, and now I've got all these different possible outcomes for x, and I have the probability associated with each one of them. All right? So I can almost think about this as like an x-y pairing. Here's my x-axis, the number of the different possible outcomes for this random variable, this discrete random variable, and then the probability associated with seeing each one of those outcomes. Okay? So I could graph this just like we graphed relative frequencies, right? Those relative frequencies just represented probabilities, so now I can see on a bar graph what outcomes are the most likely to occur and what values are lowest likely to occur. In fact, these have 0, probabilities of 0 of seeing 10, 11, or 12 wins. It's the sad part about being a Purdue football fan, I guess. So let's say I wanted to find the mean of a discrete random variable. Well, I have all these different possible values the variable could take on. Some of them are more likely than others. This should start to sound similar to when we had weighted means, right? We had a bunch of different possible outcomes. Some of them were more likely than others. It's just now our weights are going to be these probabilities, right? So we've got all our possible x values. We have the weights, which are just the probabilities. And so when we look at that equation for the mean of a discrete random variable, it's going to be you simply add up each outcome multiplied by the probability it occurs. Now, what happened to the denominator? Well, if you think about what should be in the denominator there, it should be, right, that we have the sum of our weights. So it should be the sum of the probability of every single possible outcome. But if we add up the probability of every single possible outcome, we know those should add up to 1, right? If we take every possible outcome, add up the probabilities, we're going to have at least one of them, so the probability should be 1 there. So there is kind of a denominator here, it's just that it's 1, so we essentially can ignore it. Right? So to find the mean of a discrete random variable, it's essentially a weighted mean where we already know the sum of the weights, since the weights are probabilities, will be 1, and so it somewhat simplifies that formula. Okay? So it's just like a weighted mean, where we've got the sum of these weights down here. They're no longer frequencies, they're probabilities, and so the sum of these weights will be equal to 1. So pretty easy, I think. It's like I said, I made this a short video because this is just going to be really a review of what we did with weighted means. It's kind of like combining weighted means with relative frequencies, so combining two things we've already talked about. So what if I wanted the mean number of wins over this time period? I would go 0 times 0 plus 1 times 0.06 plus 2 times 0.03 plus 3 times 0.2, all so on and so forth, all the way down until I've got every single possible outcome, all the way down to that last outcome of 12. Once I add all those up, I'll have my mean number of wins. It's just that easy. It's just like what we were doing with weighted means. Now, what if I wanted to find the variance? Well, it's going to be very similar to a weighted variance. I'm going to take every possible outcome, subtract that mean that I found. So remember, this represents the mean of my random variable x, sometimes called it like an expected value, right? That's one thing I kind of glossed over, but because, right, we're going to see, if I think about the number of wins, I'm going to see this next year they're going to win 5 games or 4 games or whatever it is. But I can only see one of those values, so I could get like an expected value of 5.1. I can't see that as an actual outcome because this is a discrete random variable, right? It has to take on integer values. So that's why we call this kind of the expected value. Right? So what if I wanted to find the variance? Oops, my mouse is crazy. I'll take each outcome, I'll subtract that expected value or mean that I found for my discrete random variable. I'll square that deviation and then multiply it by the probability that I saw that outcome for x. So it's identical to what we did with weighted variances. It's just now we don't have a denominator. Once again, the denominator should be the sum of our weights, but our weights are probabilities, and we know the sum of the probabilities for every possible outcome has to be 1. So it's really like a weighted variance, but simplified, right? Same kind of rules apply as always. If we have the variance of this discrete random variable, to get the standard deviation, we would just take the square root. Okay? So I go back to my example here. I've got it written out, but I'll just kind of walk through the process. I'll take the first outcome 0, subtract 5.14, square it, multiply by the probability I saw that outcome of 0, which is the probability 0 there, so that one's easy. Add to that the next outcome 1, minus the mean squared times the probability that we saw 1 win. Add to that the next outcome of 2 minus the mean squared times the probability we saw 2, which is 0.03, so on and so forth. All right? So really this is nothing new. It's just kind of a different spin on old things that we've talked about. It's a weighted variance where it almost becomes simplified because the weights are probabilities. So yeah, we first had to find the mean of 5.14, but then we're going to be using kind of our weighted variance equation. Okay, so the denominator is easy here too because the sum of our weights will always be 1. So we get some value. If we want to find the standard deviation, we would take the square root of this. I'll walk through a couple more examples. I think this is relatively easy. That's why I'm kind of going through it quick. So here I've got the different bonus amounts you could see: 0, 3, 6, and 10. So a discrete random variable can only take on 4 values. Each one has a probability associated with it of seeing, right? So 3 is the most likely, and then 10 and 0 the least likely. So first of all, if I'm just looking at this and I'm thinking about the answers, these are in the millions. So to see a mean of 250,000, it would have to be that this outcome of 0 was very, very likely. And it's not. It's not even this. That's the third most likely. So if we look at this, we can probably think 3 and 6 million are going to carry the highest weight when calculating this mean. And so my guess is, if I'm thinking about it that way, my mean's probably somewhere between 3 and 6, so it probably really makes sense that C or D is the correct answer here. But if I want to actually walk through it, what would I do? Well, I'd take the first outcome of 10 times the probability of 0.15, add to that the next outcome of 6 times 0.25, plus 3 times 0.4, plus 0 times 0.2. Right? All right, so if I do that right, we're thinking about what that looks like. I'm just taking all those values. Let's see if I can remember these values without looking at it. So I've got 10 times 0.15 plus 6 times, was it 0.25 plus 3 times 0.4 plus 0 times 0.2. I believe if I enter that into my calculator, I get about exactly 4.2 million, right? And so that's kind of the process for finding the answer. Very easy, just like the weighted mean we were doing before. It's just now we don't even have a denominator to worry about because the sum of those weights will just be 1, right? And we can prove that here. 0.2 plus 0.6 plus 0.25 plus 0.15 is 1. So we got that mean of 4.2, all right? What if I wanted to find the variance, all right? So if I want to find the variance, I'm going to go through, I'm going to use that mean I found earlier. I'll take the first observation, 0 minus 4.2, square that value, and then multiply by the probability I saw that outcome 0. So multiply it by 0.2. So we're thinking about what that looks like if I'm writing that down. Knowing that that mean is 4.2, I'll take 0 minus 4.2 squared. What was the probability that I saw a 0 occur? 0.2, I think, yeah. Add to that the next outcome of 3 million minus that mean of 4.2 squared. What's the probability I saw 3 million? 0.4. And then just keep doing that for every possible outcome. Once I add all those up, I should get 9.96 if you're just trying to kind of check if you're wanting to work along with this and try to check your answer. Now, if I just look at these, which one doesn't make sense at all? I'm still finding the variance of a variable, right? It's still a variance, and so variances can't be negative. We could rule B out right away, okay? So once again, don't lose sight of the bigger picture. It's still a variance, so it has to be 0 or higher. In fact, we know that it can't be 0. For a discrete random variable, for the variance to be 0, you would have one outcome that has the probability of occurring of 1. Right? We don't have that here, so we know it has to be something greater than 0. Okay, if we go through and calculate, sure enough, it's 9.96. So that was just a quick recap, like a quick little overview of what discrete random variables. They can take on only like a small set of specific values, typically integers, and we really treat them in terms of calculating their mean and their variance. Treat them just the same way we would a weighted mean, weighted variance example. But it actually gets simplified because that denominator now, the sum of those weights, since our weights are probabilities, will always be 1. Okay? I'm going to post something that I recorded not just for this section, but other sections as well, an additional example for Bayes' theorem now. So I would suggest watching that. It gives a little bit more board work than maybe someone I did even in class, and a pretty relevant example. Okay? Other thing I would do, and I'm kind of doing this one on the fly, but I think it'd be a somewhat interesting example. So let me see. I'm going to Google search COVID false positive rate. I think this was the one that I was looking at earlier. Yeah, so here we've got some information. So probably a little bit small, but you're going to have to kind of trust me, and I'll start to kind of write this stuff down for us. All right? So let's say what we're interested in, and we'll think about this in a couple different ways. So let's say I want to know, given that I see a positive test result on a COVID test, what's the probability the person actually has COVID, right? So given that the test comes back positive, what's the probability that the person actually has COVID, right? So this is my S, this is my E. Right. I would then have to rewrite this in the context of Bayes' equation. So if I look at Bayes' theorem and wrote this out in the context of my example, the first thing would be take the probability of the first state of nature, so COVID positive, times the probability of E, test comes back positive, given they actually have COVID. Now the first part of our denominator is the exact same thing, so I might write this a little bit smaller, just so I leave myself some room. Then you'll add to that the probability of the second state of nature, which is that, and I'll get out of the way in a second, that they're COVID negative times the probability of the outcome of the test we're interested in, given that second state of nature. Okay? So now we just have to work on finding these probabilities. So the very first thing is, what's just the general percent of the population that has COVID at any one point in time? So let's look. Let's look at this. So we got different percentages here. Looks like they're all right around 5%. So let's just use 5% for that. Okay. So I'm going to say the probability that if I selected a person at random that they have COVID is about 5%. Right? So everywhere I see COVID positive, I could plug in 5%, which would also mean the probability that someone chosen at random is negative for COVID is 0.95. Now the other thing I'm going to need is, given that they're COVID positive, what's the probability I see a positive test result, right? So if I go here and look at my other source, it says, I'm thinking about people that have the disease who actually get a positive result. Well, here it's telling me people that have the disease, where is it? False negative, right? And get a negative result is pretty wide range, right? So when I'm told, I was told this by when I got mine, I was told it's as high, I was told it's like 30%, right? I'm not going to read this whole thing. So let's just take kind of the middle range here. Let's use 20%, okay? So that was telling us, given that they are HIV positive, the probability they actually get a negative test result is about 0.20, which would mean the probability that they get someone that has HIV actually gets a positive, HIV, that probably that someone that has COVID actually tests positive is 0.80. Now the other thing that we don't have yet is, given that they're COVID negative, what's the probability that a test comes back positive? Right? So if I look here, this says that it's 5% or lower. We'll use the highest amount, which is 5%. Right, so 0.05. And now I have everything I need to find what I originally wanted. Right? So I'm just going to plug all these values in and then kind of use my calculator or Excel. So I'm actually going to pull up Excel here so I can see this. Actually, might just be easier for you guys. I'll just write this on the board. We'll kind of plug all these values in. Right? So the probability that someone has COVID, any one person at random, is 0.05. 0.05. Probability they are COVID negative, 0.95. Given that they have COVID, they probably get a positive test result right here, 0.8 and 0.8. Given that they don't have COVID, they probably get a positive test result, 0.05. Okay? So I now have all the values. It's just a matter of kind of plugging away and getting this entered into my calculator. So with that in mind, let's see what it actually is. Let's go to Zoom here so you guys can see this a little bit easier. So it was on our numerator, we had 0.05 times 0.8 divided by 0.05 times 0.8. And these are just numbers I'm grabbing. If you go back and look at the board, these were the numbers that I had written on the board. This was not the number I had written on the board. There we go. So we get about 45%, right? So given that somebody gets a positive test result, the probability they actually have, if they told you, I have a positive test result, the probability they actually had COVID, if we made every single person get tested, would only be about 45%, right? And it's similar to when we talked about the HIV example today, and it's that, well, look, the probability you actually have is so much lower that that you don't. If we tested everybody, these false positives end up being quite like a large number of people, right? And so we're going to have way more, these underlying these probabilities, we can also think about them as frequencies. And so you're going to have way more people that have false positives in terms of the number of people, because there's just more people that don't have the disease. So that's kind of a fun example, like where we can take Bayes' theorem, write it out in the context of our example. We can look for these different probabilities that we don't have. Like I just grabbed those from some Google searching and looking at some of the medical kind of literature that's out there. Now, I don't know how accurate these numbers might be a little off, but I doubt they're too far off. That was like a pretty reputable, right? Who was this? Harvard Health published medical school. Like I'm gonna kind of believe them, right? Like it's a pretty, and then the CDC was the one that we used for this. So, kind of a fun example of Bayes' theorem. Just a couple more examples, get some practice with it. We'll start with discrete random variables on Monday, and hopefully this kind of helped give you some more examples, a better idea about how we would solve some of these problems using Bayes' theorem.